My KCET 2026 aspirants, welcome back to our Sankalp series, right? So in this series, we are committed to get a top rank in KCET 2026, and the journey today starts with the first chapter of chemistry, that is solutions, right? So this chapter is very easy as well as highly scoring chapter. Means this is very easy to learn. Okay, you just have to invest your time in understanding some basic concepts and formulae, and then in exam this question has a very high weightage both in KCET as well as in PU. Right? So yes, let's start this journey, let's start this chapter with full confidence and clarity, and I can guarantee you that if you attend this particular lecture, this particular series, and this chapter will be completely crystal clear for all of you, and also you will be able to solve each and every questions within fraction of seconds for this chapter, right? So yes, let's get started, and please sit with a notebook and pen. Also open your NCERT book so that you can know what all topics I am covering, and you should be making notes while preparing with this, okay? And if you are on the lazy side, you don't want to prepare notes and all, do not worry, we will be providing you this in our WhatsApp channel. So please do not forget to join the WhatsApp channel. The link is there in the description section, right? Okay, now my all students, let's get started. I have tried to make this PPT little bit colorful for all of you so that you don't feel bored while teaching. So we have this chapter for 7 topics. Okay, you can see there are 7 topics. There will be 2 parts of this chapter. I will make the videos in 2 parts. In the first part, what all things we are going to cover? Let's see. In the first part, we will see types of solutions. Okay, then we will talk about concentration terms. Next, we'll talk about solubility, vapor pressure, ideal and non-ideal solution. So these 5 topics will be covered in this particular chapter, in this particular video. Okay. Now, moving forward, we have here. Okay, so here also I want to draw your attention towards something, that why you should trust our YouTube channel. Okay, we have been producing, like, this channel is very new and we started just 1 year ago, and 1 year, hardly 1 to 2 years, and students have completely relied on us and have got wonderful results. Okay, so the proof of that is here. You can see we have Prajwal S of 171, Kiran Kumar 443, Diksha C 693, then you have Samiksha for 752, Sachin 934, and all other students rank is you can see here. And I want that some of you who are listening to me, who are studying from this channel, to have your photo in this section, KCET 2026 topper, right? So it can be possible if you follow us seriously, if you watch our series every day, prepare notes every day, do question practice with us, then that is definitely possible. Now let's go to the first topic, that is types of solution. In types of solution, first, before understanding what is solution, let us talk about what is a solution made up of. So a solution is basically made up of 2 things. One is your solute and the other one is solvent. Right? So now when there is a solute and solvent, ma'am, how to distinguish between them? So this is a very easy way to distinguish. So solute is something which is present in less amount. Okay, solute is present in less amount. And what is solvent? Solvent is something which is present in more amount. Okay, I'll give you an example. Suppose you are preparing lemon water. Okay, it's very hot and sunny day. You want to prepare lemon water for your guest. So what you will do? You will take 1 glass of water and squeeze few drops of lemon in that. So lemon drops are present in less quantity. So that is your solute, and water, with the 1 glass of water which is present in more quantity, will be your solvent. I hope this is clear. Now moving forward to types of solution. So we have basically 9 types of solution. How many types? Remember this number. We have 9 types of solution. Okay, 9 types of solutions are present. Now how to remember that? See, you have to make three phases, we know: solid, liquid and gas. So the solvent, if the solvent is solid, then we call it solid solution. If the solvent is liquid, we call it liquid solution. If the solvent is gas, we call it gaseous solution, right? So you can see here gaseous solution, you can see the solvent is gas, liquid solution, solvent is liquid, solid solution, solvent is solid. And what are the solutes here? You have to take alternatively each phase: gas in gas, liquid in gas, solid in gas. Then you have gas in liquid, liquid in liquid, solid in liquid. Then you have gas in solid, liquid in solid, solid in solid. And here are the examples of these all solutions. Okay, so you can remember these examples. This will be asked in your MCQ questions. So for example, it will be given mixture of oxygen, nitrogen is an example of what? Solid, liquid, liquid, solid. So many certain examples can be given. So these examples you have to remember. Okay, take your time, like 1 or 2 examples every day. Many of the things you can easily guess. For example, oxygen and nitrogen, you can see both the gases are there, so it will be gas and gas. If you see chloroform and nitrogen, so chloroform is liquid, gas, nitrogen is gas, so liquid in gas. Camphor in nitrogen, camphor is solid, nitrogen is gas, so solid in gas. Then you have gas in liquid, so oxygen in water. You have liquid in liquid, ethanol in water, solid in liquid, glucose in water, right? So it is easy to guess, so don't have to be very consciously, you can remember aram se. Okay, now let's move forward to some concentration terms. This is very, very important. I have already discussed this part in the bridge course. If you haven't watched that, you can watch that once again. But yes, this is something very important, that is your concentration terms. Now, what is concentration terms? I told you that now we have a solvent, we add a solute to that, and that forms a solution, right? Now, how much solute is present? How much solute is present in the solution, that is given by concentration terms, right? So what is the work of concentration terms here? Concentration terms tells about the amount of solute in solution. Okay, amount of solute in the solution. I hope it is visible. Okay, amount of solute in solution. Clear? So just a minute. Yeah. Now let's see the first concentration that we have is mass percentage. Now what is the formula of mass percentage? Mass of the solute by total mass of the solution into 100. Mass of the solute by the total mass of the solution into 100. Mass of the solute by total mass of the solution into 100. Now suppose here is very example, suppose I write 10% NaCl. 10% NaCl. Now what does this mean, 10% NaCl? Let me just take some other color. 10% NaCl means 10 gram of NaCl, right, in 100 gram of solution. 10 gram of NaCl in 100 gram of solution. You can see this. Okay. Now we will go to next one, volume percentage, very similar to this one, volume of the solute by total volume of the solution into 100. Okay, volume of the solute by total volume of the solution into 100. Next we have mass by volume. Here it is mass of the solute by volume of the solution into 100. You can see the difference. Mass percentage means mass by mass. Volume percentage means volume by volume. Mass volume percentage means mass by volume. Clear? Now we'll go to the next important here, mole fraction, molarity and molality. So mole fraction is the number of moles of the solute by the total number of moles, and it is denoted, for example, you have a number of moles of A. For example, you have number of moles of A and number of moles of B. Na and Nb is there. Then what's the value of mole fraction of A? It is number of moles of A divided by total number of moles. Right? And what is the Nb also? Nb by Na plus Nb, that will be mole fraction of B. Now what is the total mole fraction? You should know this relation. Xa plus Xb will be equal to 1. Okay? Clear? This I have already discussed in bridge course. If you haven't watched, Please have one more look there. Next, coming to molarity. Molarity is what? Number of moles divided by volume of the solution in ml into 1000, right? So this number of moles you can write it as given mass by molar mass, W2 by M2, right? So what will be the molarity formula if I write like this? Molarity is equal to W2 by M2 into 1000 by volume in ml. Now whose volume? Volume of the solution. This is important, okay? Volume of the solution. Next you have molality. Molality is what? Moles of the solute by mass of the solvent in gram into 1000. Moles of the solute by mass of the solvent in gram into 1000, right? Here also in place of moles you can put this W2 by M2, okay? Fine. Now we will go to the third topic, that is solubility. Solubility, we will be talking three terms here: solubility of solid in liquid and solubility of gas in liquid, okay? So the solvent is liquid here, and we are discussing two types of solute. One is when we are dissolving solid in liquid, and another one when you are dissolving gas in liquid. Now this dissolving of gas in liquid, we have so many examples, right? You have seen your carbonated drinks, right? When you open the cap of a cold drink, you can see carbon dioxide coming out, right? Effervescence we observe. That is because the gas is dissolved in the liquid. So the various factors regarding all this we will be studying. So basically we have two things: solubility of solid in liquid, gas in liquid. Solid in liquid, what are the examples? You have salt solution, sugar solution, glucose solution, right? These are all solid particles which we dissolve in water, right? So now let's go to the first one, solubility of solid in liquid. So we have, first we will see what all factors affect the solubility of solid in liquid. On what factors it depends, okay? So the first factor here is nature. Now here a very important thing is like dissolves like. This line is very important. Like dissolves like, okay? So we have what are the two things we are talking about here? Solute and solvent. So if the solute and solvent are of same nature means polar and non-polar. If solute is also polar, solvent is also polar, then polar they will dissolve, means solute will dissolve in the solvent. If solute is polar but solvent is non-polar, right? Solute is polar, solvent is non-polar, then there will be no dissolving. For example, you can take ethanol. Ethanol, what's the ethanol structure? Or methanol. Let me take methanol. Here this one, delta minus, delta plus, so there is a charge difference, so it is polar. And water, if you see, right, water is also polar, this is also polar, so ethanol will dissolve in water. But if I talk ethanol and benzene, benzene is non-polar, right? So that means this ethanol will not dissolve in benzene. Why? Because this is non-polar. So that is the concept here, that polar dissolves polar. Salt and sugar are soluble in water. Naphthalene and anthracene. Naphthalene and anthracene, if you see, naphthalene structure is like this. Okay, sorry. It's a means it's also a non-polar molecule. Okay, so okay, just a minute. Okay, so yeah, so naphthalene and anthracene both are non-polar, and benzene is also non-polar. So non-polar will dissolve in non-polar. So this is how you make friends in class, right? Generally what happens? You make friends with those people who are of your mentality, whose nature, whose behavior, whose thought process is similar to yours, right? So like that only, even solute and solvents make friends with like people. So if solvent is polar, solute should also be polar. If solvent is non-polar, solute should also be non-polar. I hope you are getting this one. So the first factor which affects the solubility of solid in a liquid is your nature of the substance, right? Next factor is what? Very important. Can you guess by seeing this diagram? It is, yes, it is your temperature. Okay, so how does the temperature is affected? So now when you dissolve a solid in a liquid, either it can be an endothermic process or an exothermic process. We cannot say that it is always endothermic or it is always exothermic. It can be either endothermic or exothermic. So then you have to apply Le-Chatterley principle. If it is endothermic, if you increase the temperature, solubility will increase. If it is exothermic, if you decrease the temperature, solubility will increase. So you can see here, if it is endothermic, how do we represent endothermic? Delta H is greater than 0, right? So if it is endothermic, it increases, solubility increases with temperature. Okay. Next, if it is exothermic, decreases with temperature, means if you increase the temperature, solubility will decrease. If you decrease the temperature, solubility will increase. Next, last factor we have is pressure. Okay, pressure. So solids do not have any effect, or pressure do not have any effect in the solubility of solid in a liquid. Okay, pressure has no role. So we have just two roles: nature of the solvent and temperature. Like dissolves like, and in temperature, if the dissolution is an endothermic process, then if you give more heat, more solute will get dissolved. If it is an exothermic process, if you decrease the temperature, then the solubility will increase. I hope this is clear. Now let's move to the 3.2, that is solubility of gas in liquid. Here we have only two factors. The first one is definitely temperature. So now just imagine, okay, why do we always want to have cold drinks or cold beverages? Right, when you go to any shop and we want cold drinks, we want that it should be cold in temperature, right? What's the reason for that? If you have observed that if you have kept the cold drink, for example, you have purchased a Sprite bottle, okay, and you have kept it open, you haven't kept it in fridge, you have kept it at room temperature for some 3-4 days. After that, if you see that gas feeling, you know that one burning sensation we get, the gas that is dissolved, that feeling you won't get, you just feel like it is a sugar and water solution, you will feel like that. So what can be the reason for this? And if you keep that same bottle in fridge for 3 to 4 days, and then if you see, there will be slight, the feeling of that burning sensation will still be there. So that is because of temperature. So when the temperature is less, solubility will be more. Just imagine the reason for that. Gas particles, you know, these are highly energetic particles. If the temperature is high, so what will happen? These gas particles will collide with each other, their energy will increase, their kinetic energy will increase. So what they will do? They will escape. But if the temperature is cold, okay, if the temperature is low, these gas molecules are not very active, okay, they are having less kinetic energy, so they cannot escape, they will be in the solvent. So we have very clear conclusion here. If the temperature is high, solubility will also increase, solubility will decrease, and if the temperature is low, solubility will increase, right? For gases, can we guess that it decreases with the increase in temperature? If you increase the temperature, solubility will decrease. Next factor, we have pressure. Just imagine this one, you have a container, there are gas particles there. If you compress it, if you put more pressure, these gas particles will enter into the solvent, okay? So that is why, and can you, here also I'll give you the cold drink example. When you open the cap, why we get that effervescence? What is the reason for that? So now see, you have a cold drink bottle, right? So in this cold drink bottle, the gas is dissolved with high pressure. It is sealed under high pressure. Now when you open the cap, you are releasing the pressure. So if that pressure, this is the, suppose, see, this is the container, okay, these are the gas particles. Under this some pressure is there. Once this pressure is released, this gas particles comes out fast, and that is what we observe as effervescence, right? So pressure, what I can say, pressure, if you increase the pressure, solubility will increase. So solubility increases with the increase in pressure, solubility decreases with the increase in temperature. I hope the effect of pressure and temperature is clear for all of you. Okay, now this effect of pressure we will study in detail. Okay, there's a particular law to describe this one. We'll be studying in detail about this effect of pressure. That law which I was talking about is your Henry's law. Okay, Henry's law. What does Henry's law say? Very simple thing, what we have discussed just now. Henry's law says that the solubility of a gas in a liquid depends on the pressure above the liquid. How much pressure you have. If you have more pressure, you will give more pressure, more gas will get soluble. If you have less pressure, less gas will be soluble. That is what is Henry's law. So what we can say, now see here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 particles are here, and we have how much particles in the solubility? 1, 2, 3, 4, 5. This is the pressure, okay. Now when I increase the pressure, you see force is applied. When you increase the pressure, okay, when you increase the pressure, what will happen? These particles will get inside the water, or will dissolve more. So now here you can see more number of particles are dissolved, here less number of particles are dissolved. What is the reason? Here pressure is less, here pressure is more. That's Henry's law, very simple. You should remember the statement because it can be asked in the exam. In PU exam, definitely it is a very, very predictable and most important definition. So you should know what is Henry's law. What does it say? Solubility of the gas in a liquid. Solubility of the gas in the liquid is directly proportional to the pressure on the liquid surface. Directly proportional to the pressure on the liquid surface. How do we represent that? So I can write this one, see. Solubility of the gas, or I can solubility of the, now I represent solubility as mole fraction, okay. Solubility of the gas is proportional to the pressure, okay, or I can say pressure of the gas is proportional to mole fraction of the gas, right. Now what I can do, I hope this is visible, yes. So to remove this proportionality, we have a constant that is called as Henry's constant, okay. So the formula becomes P of the gas is equal to KH into X of the gas. What is this KH here? KH is Henry's constant. Okay, KH is Henry's constant. Okay, I hope you are visible. I think little bit light, but yeah, you can manage, I hope. Okay, KH is dot X into gas. Clear? Fine. Now what we have to discuss? Okay, now there's something very important. So X represents what? This X represents is solubility. Now what I can write this equation? See, I'll write here. I can write that X of the gas is equal to pressure by KH, right? So can we say here that the solubility and the Henry's constant are inversely proportional to each other? Okay, so here one in important conclusion we have, let me just write down this one. So I have here solubility is inversely proportional to Henry's constant. Please note down this one, this is very, very important. Solubility is inversely proportional to Henry's constant. Here many times KCET also questions ask, they will give you 4 gases, their Henry's law constant will be given and you have to predict which is more soluble, which is less soluble, right? How to do that? You know, if the Henry's law constant value is high, then solubility will be less. If Henry's constant is low, then solubility will be high. Okay, so this is our Henry's law. Now let's move to application of Henry's law. Okay, this is very, very important. Already first application I have discussed, that is your carbonated beverages. Here what happens, to increase the solubility of the carbon dioxide in soft drinks, we give huge pressure. Okay, and that is why when you release the cap, you release the pressure and the gas comes out in the form of effervescence. Okay, that's the first application. Second application is in the scuba diving. So just I want all of you, those students who are watching this video, to give me an answer of in the comment section that have you ever tried scuba diving, or are you willing to try scuba diving in your life? Just put down in the comment section whether you have done it or not, or if you are interested or not. So let me share my experience with you. So I have done this scuba diving last year only, right, in Andaman. I tried to do that. So let me share my experience with you. So last year only I had this scuba diving. Okay, so here what happens actually, you feel that when you go deep inside the water, okay, what happens, the pressure increases. Now just now we saw that if pressure increases, solubility of the gases will increase. So what happens, the gases inside the different gases, oxygen, nitrogen, gets dissolved in your blood. Okay, now when you come to the surface, okay, after scuba diving, when you come to the surface, the pressure is less. Now see, suppose this is the water body, okay, and you are starting your scuba diving. So you will be here, right? When you are here, you have pressure of this much. Okay, this much pressure is on you. So the air pressure. So when the pressure is high, what will happen? The gas solubility will be more and more gases will dissolve in our body. Now once you complete your scuba diving and you come to the top, okay, then the pressure will be less, right? Pressure will be less. If pressure is less here, then what will happen? Solubility will decrease. So all the gases that had dissolved in your body will try to come out now. When it tries to come out, it will come out in the form of effervescence, bubbles will form, and now these bubbles can block your arteries and veins, and that is why there is a medical condition here, or there will be huge pain in your body, a medical condition called as bends. Okay, so to prevent this, what we do in the tanks of, in the oxygen cylinder tanks of scuba divers, we add a small amount of helium. Okay, we add a small amount of helium. Now what is the role of this helium? The KH value of helium is high. If KH value is high, solubility will be less. So in the tank, the solubility of the gases can be reduced by adding helium to the tanks of the scuba divers. Okay, clear? Now let's go to the third application. Third application comes to the climbers, mountaineers. Okay, so we are in the today adventure zone. Okay, we have done scuba diving. Now let's go and climb the Mount Everest. So when we do mountaineering, okay, so you see, suppose this is your Earth's atmosphere. Okay, see, this is your Earth atmosphere, for example, and this is mountain. Okay, and we are, suppose this is the ground level. Okay, so ground level we have this much pressure. Now when the mountaineering or the person climbs the mountain, for example, it has reached here. Here there will be less pressure, less atmospheric pressure. Now if the pressure is less, solubility will be less, right? So less amount of gas is dissolved in the blood of this person, less amount of oxygen will be dissolved. So if less amount of oxygen is there, then can we survive? We require proper amount of oxygen for our body to function. Now because of this less pressure, what happens? The body gets less oxygen and we feel difficulty in breathing. The brain doesn't work properly because oxygen doesn't reach. So that is why we have to carry oxygen cylinders, and at this point there may be some medical problem, and this problem is called as your anoxia. Okay, so we have understood what is bends and this medical condition where you feel that your nausea or some dizziness, okay, you are not able to, your senses are not working properly, that is called as anoxia. Okay, three applications of Henry's law is clear. One is the carbonated beverages, when you give more pressure, more gases dissolved. Second one is scuba diving, and third one is climbing, right? Okay, let's move forward to the fourth topic, that is vapor pressure. Okay, a very important topic, and most of the questions we have to deal with this particular topic. Now vapor pressure, will be studying three things under that. What is vapor pressure? Vapor pressure in liquid solution, there I will introduce you to our Raoult's law, and then we have vapor pressure in liquid solid solution. This, if you have understood, this is very easy. Okay, so let's move. What is vapor pressure? So you understand what is vapor, what is pressure. Okay, so pressure given by vapor is vapor pressure. So let's understand. Suppose you have a closed container. I hope this is visible. You have a closed container. Okay, now what will happen in this closed container? Evaporation will definitely take place, right? So some particles are evaporating. Okay, some gas particles, these red particles are evaporating. Now when these particles evaporate, they hit the container, right? They cannot escape here because it is a closed system. So these particles will hit the container and then again it will condense back, right? So this process continues. So just let me give an example. So this process will continue. See, you have particles here. Okay, suppose 4 particles are present. Now suppose at one point of time what happens? 3 particles are evaporating. Okay, so what I will have in the vapor phase, I have 3 particles. Okay, so now what you can see, or let me just take some more particles. We have 1, 2, 3, 6 particles are there and 3 particles have evaporated. Or let me just add some more. Yeah, 8 particles are there, 3 particles are evaporated, right? So what will happen? I will erase these 3 particles because these 3 have undergone vaporization. Now what will happen? After some time there will be a stage where suppose number of particles evaporating and number of particles condensing will become same. So what will happen? For example, you can see that in the vapor phase and in the liquid phase. In this vapor phase now I have 3 particles, in the liquid phase I have 5 particles, right? Now what will happen? Suppose 1 particle evaporates now. At the same time 1 particle will condense here. So when this 1 particle evaporates and 1 particle condense, the number of vapor phase will still remain same, number of particles in the liquid phase will also remain 5. So there is a point where the rate of evaporation, there's a point where rate of evaporation is equal to rate of condensation. Okay, the evaporation is the number of particles going to the vapor phase and the number of particles coming to the liquid phase. The rate of evaporation and the rate of condensation are equal. Okay, means see, this number may be different. Like here you can see 1 particle is evaporating and 1 particle is coming down, right? So this rate becomes constant. So if this rate becomes equal, what will happen? The vapor phase and the liquid phase number of particles will remain constant. Suppose 2 is going, 2 is coming down, 3 is going, 3 is coming down. The concentration of vapor and liquid phase will remain constant. So that is the point where we are talking about equilibrium has attained. What is there? Equilibrium. Equilibrium between what? Equilibrium between the vapor phase and the liquid phase is attained, right? Now once this equilibrium is attained, what will happen? These vapors are there, they are gaseous particles, they will collide with each other, they will collide with the glass container. So at this point of time, when the equilibrium is reached, whatever pressure is applied by these particles, on the liquid surface is called as your vapor pressure. I hope this is clear. Let me explain once again. If you have already understood, please forward, okay, just go to the next topic. Let me explain. You need a closed container, okay, in that you have taken some water or any liquid. Now these liquid will create vapors. Since the container is closed, the liquid cannot evaporate, the vapor particles cannot evaporate, they will hit the container and come back and condense. So there are 2 processes going on, rate of evaporation and condensation. Once this process goes on, after a certain time there will be a point where the rate of evaporation will be equal to the rate of condensation. Now when this stage has been reached, we call that equilibrium is attained. And at this point of time when the equilibrium is attained, the pressure exerted by the vapors on the liquid is called as vapor pressure. I hope this is clear. So very simple, vapor pressure exerted by the vapors. But what you should remember, that this pressure should be exerted by the vapors when the system is at equilibrium. Now ma'am, what is the system at equilibrium? When the rate of evaporation is equal to rate of condensation. I hope this is crystal clear to all of you. Okay, so now you can see at equilibrium the evaporation rate equals the condensation rate. Okay, so the molecules in the vapor phase collide with the walls and the lids of the container, causing pressure. Evaporation and condensation occur at the liquid surface. Increasing the temperature increases the rate of evaporation and increases the vapor pressure. Now if I increase the temperature, more number of particles will evaporate, more number of particles will be there in the vapor phase, so they will include more pressure. Okay, so vapor pressure is the equilibrium pressure of a vapor above its liquid or solid state. Okay, so now once we have understood this vapor pressure, I will introduce you to Raoult's law. Okay, very similar to Henry's law. Okay, but here we are talking about liquid solution. So just imagine that this is a solution where we have 2 types of liquid, red particles you can see and green particles you can see. So these red particles are solution A or solute A you can see, green particles are solute B. Both the particles can evaporate. Okay, means they are volatile. When I talk about volatile solute, volatile component, that means it is something which can evaporate. So red will also evaporate, green will also evaporate. So vapor pressure or the pressure due to A will also be created. And one more condition let me apply here. This container is closed. It is a closed container, right? So this container is closed, so molecules cannot escape. Okay, closed container, please mention this one, it's a closed container. Now see, there will be vapors of A here, vapors of B will be there, pressure due to A will be there, right? Pressure due to vapors of A will be there, pressure due to vapors of B will be there. So the Raoult's law says that the pressure exerted by A, the pressure exerted by the vapors of A will be proportional to the mole fraction of A in the solution. That is very, very simple thing. Now see, first understand what is the law here. Yeah. Okay. See, suppose I have A particles. Okay, and then I have B particles. Now, you see here, now these A will create vapor, A particles will create vapor. Since the moles, the number of the particles of A is more, vapors of A will also be more A will evaporate, more A pressure will be created. So I can say that the pressure created here by A is proportional to the mole fraction of A, right? Similarly, here since B less is there, less vapors of B will form, less vapors of B will form. So I can say that pressure of B is proportional to mole fraction of B. That is what is Raoult's law. Okay, so let's see this in detail. For a solution of volatile liquids, the vapor pressure of each component, vapor pressure of A, vapor pressure of B, vapor pressure of C, vapor pressure of each component is directly proportional to its mole fraction present in the solution. Pressure of A is proportional to the A present in the solution. Pressure of B is proportional to the mole fraction of B present in the solution. So how can we write it? So you can write down PA is proportional to XA. Okay, and to remove this proportionality, we multiply with a constant here. This is actually right like this, PA, sorry, 1 second, yeah. So this is like this, PA is equal to P naught A XA. Okay, P naught A XA. I hope this is visible. Okay, P naught A XA, right? Now what is this? P naught A? P naught A, just write down here, P naught A is the pressure of A. Okay, P naught A is the pressure of A, pressure of pure solvent A. Okay, pressure of pure solvent A. P naught A is equal to pressure of pure solvent A. Now what is this one? See, when I have, so let me just explain again. Yeah. So when I have only A particles here, okay, there is no B, only A particles here. So this will create some pressure, vapor pressure will be created. So this pressure is called as P naught A. Pressure of A due to when pressure due to A when only A is present. Okay. Now when I have here both A and B, you have A particle also and you have B particles also. Okay. At that time, whatever is the pressure created here due to A, this one, this is called as your PA. Okay. P naught A and PA is different. PA is the partial pressure, means when you have more than one component, I talk about the pressure exerted by one component, that is PA. When I have only A, there is no other component and the pressure exerted here is called as P naught A. Now what I can say here, P according to Raoult's law, PA, the pressure exerted by A is proportional to the mole fraction of A. Right? To remove this constant, we have PA is equal to P naught A XA, right? P naught A XA. Okay, so that is what is there here. Raoult's law, PA is equal to P naught A XA. So please just write down here, small typing error is there. So PA is equal to P naught A XA. Okay, understood what is P naught A? Now we will move to Dalton's law. So I will explain this graph afterwards in detail. So what is Dalton's law? Now see, we have Dalton say that the total pressure, you have A also, you have B also, so total pressure will be there. Total pressure will be equal to partial pressure of A plus partial pressure of B, right? Now partial pressure of A, how can I write? P naught A XA plus P naught B XB. This is your P total. Okay, this is the formula that we will be requiring again and again. P total is equal to P naught A XA plus P naught B XB. Okay, this graph we will talk in detail after some time. Clear this one? Okay, so now if there is third component, P naught A XA plus P naught B XB plus P naught B XC. Okay, so Dalton's law is this one. Dalton says that if there is vapor pressure of A also, vapor pressure of B also, then the total pressure will be equal to PA plus PB. Okay, and PA is P naught A XA, this is according to Raoult's law. PB is equal to P naught B XB, this is according to Raoult's law. Okay, clear? Now let's move to the next thing, vapor pressure for liquid solid solution. This is very interesting. Now when you have a liquid, okay, you added some solute particles to that, solid solute particles. The previous one was liquid solution. This is a liquid solvent to which you have added a solute which is solid and non-volatile. Okay, means it is not going to evaporate. So now what will happen? See, if there is a pure solvent, okay, now you can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 particles are there in the surface, and we have these particles to evaporate. These 10 particles can evaporate. Now if I add a solid solvent which is non-volatile, then what will happen? The surface will be occupied by solid particles also. Now these green particles, you see earlier 10 were there, now we have 5 green and 5 blue. Now these green particles will not evaporate, right? This one will not evaporate. So only these 5 particles can evaporate now, right? So now there were 10 particles here which can evaporate, here there are only 5 particles which can evaporate, right? So what is the condition, what you understand here? The number of particles which can evaporate has become less, so that means the vapor pressure will also be less, right? So that is what you have to understand. In a pure liquid, the entire surface is occupied by the molecules of the liquid. In a pure liquid, the entire surface is occupied by the molecules of the liquid. If a non-volatile solute is added to a solvent to give a solution, the vapor pressure of the solution is solely from the solvent. Now here the vapor pressure is not contributed, or the solid particles do not contribute to the vapor pressure. Only the solvent particles can form the vapor pressure, right? So this vapor pressure of the solution at a given temperature is found to be lower than the vapor pressure of the pure solvent at the same temperature. You can see here, obviously, since more number of particles can evaporate, more particles will evaporate and the vapor pressure will be more. Now here, since we have only few particles that can evaporate, so few particles will evaporate and they will cause less vapor pressure. So whenever we add a solid to a liquid solution, the vapor pressure will decrease. Okay, so this, remember, this is very important. Whenever we add a solid solute to a solution, the vapor pressure will decrease. Okay. Next, for liquid and solid solution, so you can see we have only the mole fraction of the solvent, right? As you increase, so we have this formula, right? P is proportional to mole fraction, right? So if the mole fraction will keep on increasing from 0 to 1, the vapor pressure will increase. That is the graph for vapor pressure of liquid solid solution. Okay, so this equation we have already shown you. Okay, Now let's move to the most important topic, that is ideal and non-ideal solution. Here what all things we have to study? We have to see what is ideal solution, what is non-ideal solution. In non-ideal solution we have positive deviation and negative deviation. Then we have graph for ideal and non-ideal solution, examples, and lastly we will talk about azeotropes. So now let's start with the first topic, that is ideal solutions. Okay, so just a minute, I'll take the, yes. So first of all, ideal solution. Before understanding anything, I can assure you that this is going to be the simplest explanation that ever you can have for ideal and non-ideal solutions. Let's take this example. Suppose you have orange juice and mango juice. Okay, orange juice you have in a closed container, mango juice also is in a closed container. So orange juice is creating here 50 vapors. Okay, you can see orange juice has created 50 vapors. Then mango juice is there, 30 vapors. Okay, now you have mixed both of them in the same container. Okay, so here the Raoult say that, Raoult's law we have studied, right? So this is Sir Raoult. He said that the total vapors here should be 80 vapors, right? 50 plus 30, 80. This is a theoretical concepts. Okay, but if it is 80, then we call those type of solutions as ideal solutions, if it is 80. If it is not 80, if it is not equal to 80, then we call it as non-ideal solution, right? This, if it is not equal to 80 means it will be either more than 80 or less than 80, right? So if it is more than 80, we call it positive deviation. If it is less than 80, we call it negative deviation. Okay, so first, if the value is exactly equal to 80, then it is an ideal solution. If it is not equal to 80, then it is non-ideal solution. Now if it is more than 80, then it is non-ideal, positive deviation. If it is less than 80, non-ideal, negative deviation. Okay, so we will see here. So we are talking now, going to talk about the 5 different parameters of this ideal solutions. So examples are benzene and toluene. You are mixing in benzene and toluene, 1 liter, 1 liter. So what will happen when you mix them? This one will become 2 liter. Okay, 2 liter we will get here. Now what are the things that you should know about these things? Molecular structure. Benzene and toluene, if you know, the molecular structure should be similar. Okay, if it may not be visible, I am dictating, so please write down. Molecular structure should be similar. Intermolecular forces. Okay, the force of attraction between these molecules, the force of attraction between these molecules should also be similar. Okay, next, Raoult's law. These two solutions must obey Raoult's law. Okay, they must obey Raoult's law. Now when I am saying that they must obey Raoult's law, that means the total vapor pressure here, the total vapor pressure here, the addition should be the total vapor pressure here. Suppose it is 30, 30, it should be 60. That is what is called as Raoult's law, and these ideal solutions must obey Raoult's law. Delta V mix should be equal to 0. Means before mixing and after mixing there should not be any change in the volume. You can see after mixing 2 liter, before mixing also 2 liter. So delta V mix should be equal to 0. Delta H mix should be equal to 0. Means there should not be any heat produced or released. Whatever delta H is here, the same value of H should be there. The delta H value should be 0. So these are for your ideal solution. Now if I talk about non-ideal solution, so as I told you, 50 plus 30, suppose it is there. Now once you are mixing them, it will not be equal to 80. It can be either more or less, right? So if it is more than 80, we call it, suppose 100 vapors are there, more than 80, then we call them as non-ideal solution, positive deviation. Okay, so this is positive deviation. Now why this number of vapors have increased? So what I can say that when we have mixed them, okay, so 50 plus 30, already 80 vapors were there. Okay, now when you mix them, the another 20 vapors have evaporated, right? Another 20 vapors have evaporated. Now why these 20 vapors have evaporated more? So the reason can be that these particles do not like each other. Okay, the orange juice and mango juice don't like each other. They want to go far away from each other. So what they will do? They will evaporate. They cannot be in this closed space. They want that I want to get rid of this orange juice. I want to get rid of this mango juice. So what will happen? They will evaporate more. Now once they evaporate more, the vapor pressure created here will be more. So you can see they stay away from each other and more particles escape into the air. So this type of deviation is called as your positive deviation, where the number of vapors are more than the expected value. So here what equation I can write? I can write that, let me write here somewhere. Okay, I'll go, okay, just a minute. Okay, now let's talk about first negative deviation. Now if you have mixed orange juice and mango juice, okay, and what happens? 50 plus 30, 80 should be there. We are getting only 60 vapors. Now what can be the reason here? See, already 80 vapors were there, but they are very attractive towards each other. Okay, so what will happen? This mango juice and orange juice will come close to each other. Once they come close to each other, very close, they will form liquid, right? So they will come back to the liquid state. So there will be only few in the vapor state. So that is the reason orange and mango molecules love each other, right? So that is why they do not want to escape. They want to stay together. They want to stay with each other. They do not want to escape. So the vapor pressure decreases here. So they stay together, less particles escape into the air. So whenever we have expected values more than the observed value, it is a negative deviation. Okay. So this is all about positive deviation and negative deviation. Now we will know certain things, examples for this one. So I have taken example of acetone. Okay, acetone and carbon disulfide, 1 liter and 1 liter if you take, you will get here 2.02 liters. Okay, just an example. So what does that means? They have expanded, the volume has expanded. So here what all factors I can say for, so this is an example of positive deviation, this is an example of negative deviation, right? So what we should know, in positive deviation what happens? The total pressure is more than the Raoult's calculated value, P naught A XA plus P naught B XB. That's the first thing, right? Then what's the second thing we should know? The interactions are weaker. So we talk about A and B here, right? So I can say that AB interactions are weaker. Okay, AB interactions are weaker, the force of attraction is very less, so this more number of particles will escape to the vapor phase and the vapor pressure increases. Third thing you should know, delta V mix should be greater than 0. You can see 1 plus 1, 2, right? So 2, and if I add this one, the volume after mixing and before mixing, the value will be 0.02 liter, right? So it is a positive value. Then I have delta H mix is greater than 0. Okay, so these are the 4 things you should be knowing about a positive deviation. Example, acetone and carbon disulfide. I'll give you a list of table example also, don't you have to worry for that. Negative deviation, you have acetone and aniline. So here what happens? The pressure, the total pressure is less than P naught A XA plus P naught B XB. Okay, then you have here AB interactions are stronger. AB interactions are stronger. Okay, next we have delta V mix is less than 0, negative, and you have delta H mix is less than 0. Okay, V mix is less than 0 and H mix is less than 0. Now we will see some how to represent this one in graph. Okay, how to represent ideal and non-ideal solution in the graphical form. So first of all, I'll tell you a basic thing. You have to draw like this. Okay. Okay. So you know, according to Raoult's law, PA is PA, pressure of A is proportional to XA, pressure of B is proportional to XB, right? So I have here XA. Okay. Now XA value is from 0 to 1 here. Okay, from left, this is left side and this is right side. Okay, so XA value increases from left to right. Okay, so XA value is increased 0 to 1, it is increasing. If XA will increase, PA will also increase. So I will draw a graph like this. Okay, XA is increasing, PA is increasing. Now XA is equal to 1. Means there is no B at that point of time. What is that pressure called as? When I have only A, that is P naught A, right? So this value is P naught A. Now right side I have x for xb, it increases from right to left. Okay, so this is right to left, so I have here xb is 1 and here this side it is increasing 1 to 0. Okay, so I will write this is 0 to 1 is xa and this one is 0 to 1 is xb, right? So if it is increasing 0 to 1 like this, then the pressure will also increase like this, right? And this highest pressure when xb is completely 1 means there is no A there, this pressure is P naught B, right? Now this value here, this value is called as your total pressure, P total, which is equal to P naught A XA plus P naught B XB, right? So this is the graph you have to draw. Now what will be the graph for positive? So this one you can see here. Now what will be the graph for positive deviation and negative deviation? For positive deviation the pressure will increase, we have seen that, sorry, and for negative deviation the pressure will decrease. Okay, graphs are important, so you have to practice this graph as well. Now we will see this table. You should remember I have given a lot of examples for ideal solutions, non-ideal solutions, positive deviation, and non-ideal solution, negative deviation. Okay, so if non-ideal solution negative deviation means they have more attraction, non-ideal solution positive deviation means they have less attraction. Okay, and you have seen ideal solution as those which have similar structures or similar chemical formula, they are your ideal solutions. Okay, now we will go to the last topic, that is your azeotropes, a very interesting topic. So what are azeotropes? There are certain things that you should know. Azeotropes are binary mixtures. Binary mixtures means there should be only one solute and one solvent. Okay, the binary means two types of solutes or anything, two should be there. Binary mixtures having same composition in the liquid and the vapor phase. Okay, so means always they have same, whatever mole fraction is there in the liquid phase, the same mole fraction will be there in the vapor phase also. So same mole fraction or same composition in the liquid phase and vapor phase, and they boil at the same temperature. This is very important, boil at the same temperature. Suppose you have taken ethanol and nitric acid, they both will have the same boiling, that mixture will have same boiling point. If the mixture is having same boiling point, then can we separate them? No, right? Using distillation, if you remember or if you have a few small idea about the working principle of fractional distillation. In fractional distillation what happens? You heat the solution, the one whose boiling point is less evaporates faster, condenses and then separates out. But here both the mixtures will have one boiling point. Okay, so it is not possible to separate them by fractional distillation. So this is a very unique type of mixture and is possible only at certain composition only. You cannot take any random solution and prepare azeotropes. Okay, so these are very unique solutions. So in this azeotropes we have two types of azeotropes. One is minimum boiling azeotrope, another is maximum boiling azeotrope. Now what is this one? See, suppose you have taken A and B. Okay, A will have one boiling point, B will also have a boiling point. Now when they are forming an azeotrope, if the boiling point is more than the boiling point of each of them, then it is called maximum boiling azeotrope. If A and B have boiling point and when you mix it, the boiling point is less than the boiling point of each of them, then we call it as minimum boiling azeotrope. Okay, so let's see one example. So now see, when you will have minimum boiling and when we will have maximum boiling. See, if A and B have very strong interactions, okay, A and B are very strongly attracted towards each other, then they will not evaporate easily. You have to give more heat at that point of time, more temperature is required, so maximum boiling azeotrope will be taking place. And when we have very strong interaction, which type of deviation is that? That is your negative deviation. So negative deviation will show maximum boiling azeotrope. And when A and B will have minimum, means they will easily boil when their attractions is very weak, right? They will easily boil if the attractions is very weak. And in which type of deviation we have weak attractions? In positive deviation. So minimum boiling azeotrope is shown by positive deviation and maximum boiling azeotrope is shown by negative deviation. Okay, so we will see that here. maximum boiling shows negative deviation, and we have minimum boiling azeotrope, it shows positive deviation. And these two examples are very, very important, which you should remember. For maximum boiling, we have nitric acid, which is 68% in water 32%, and for minimum boiling you have ethanol 95% and water you have 5%. Okay, so if you take this particular composition and concentration, then you will have this type of azeotropes. Okay. So yes, that's all students in this video. Thank you everyone for listening to me with so much patience, and I hope all of you have understood all the concepts and have written notes. Okay, if not, once again I want to repeat, please join our WhatsApp channel. The link is there in the description section. And as I told you, we are going to provide you the best content that is possible. Everything will be provided on time. So the only thing you have to do is to follow our channel, and for that please do not forget to subscribe Diksha Karnataka, right? And in this video we have not done any question. Do not worry, in the next video we will be doing the most important topics and a lot of question practice. Thank you for watching. All the best. Keep studying and keep smiling.